So, good evening, students. So we have been discussing last 6 to 7 lectures on approximate method, especially for continuous system, how we can able to discretize a continuous system into some discrete number of degree of freedom, so that we can have some approximate solution. And those methods, they have different requirements. We have seen that some methods require the comparison function and some method require the admissible function. And even we found that one method which was requiring not even the admissible function and the comparison function, any function which satisfies partially some boundary condition and maybe partly some equation of motion can be used for the continuous system discretization. So with that background, now I think we have covered most of the free vibration problem, except we have not covered the two-dimensional problem, that is when we have membranes or when we have plates. So toward the end, we'll try to cover that in a couple of lectures. But before that, today we'll start another chapter on the forced vibration, or the how we can able to get the response of a system because of various kind of force. So here again we will be having the discrete system as well as the continuous system, and then when we have continuous system approach, initially we'll be having that is closed form solution, and then we'll go for the approximate method. So whatever the method we learned in the previous chapter, that will be useful here in the forced vibration also. So idea of the forced vibration in discrete system, if you recall that at very beginning we talked about the Duhamel integral or the convolution integral, that is for single degree of freedom system. Now we have talked about the multi-degree of freedom system or continuous system. So we, especially when we are talking about discrete system, using modal matrix, using eigenvalue problem, we can able to discretize the coupled equations into n number of equations which are uncoupled, and they all will be single degree of freedom system in terms of the natural coordinates. So we can able to apply to each of these equation of motions independently the convolution integral, and then we can able to obtain the natural coordinate response, and then we can again transform back them to the physical coordinates to get the response in the system in the physical coordinates. So that will be the idea based on which we'll be working. Even in the continuous system, we have seen that using orthogonality condition, we can able to discretize the continuous system to infinite single degree of freedom system. And another thing, when we take the approximate method, then we discretize the a continuous system to n number of n degree of freedom system. And once we discretize that into n degree of freedom system, then again we can decouple them using modal matrix of the that kind of approximate modeling. And once we decouple it, again we can able to apply the convolution integral to obtain the forced response of the system. So initially, in today's lecture, we'll be talking about more general approach for the forced vibration. We'll see what are the different type of forces which a dynamic system can have, and a very general approach will follow initially, and then we'll go for a specific force also. So with this background, let me share the slide. So we have so this here also we will be talking about undamped system or the force response. In this, actually, the response will be in general sense, in the sense that we can have response due to initial disturbance, that is the transient response, or response due to the steady state force. So, what is the response of a dynamic system? Response is nothing but the how the displacement of the dynamic system is changing with time, or the velocity is changing with time, or the acceleration is changing with time. So all these three quantity, displacement, velocity, and acceleration, are the response of the system. And because of some excitation, some kind of force which is acting to the system. Here again, excitation will be talking in more general initially. So we can have a deterministic response for deterministic force. So when we have deterministic excitation, that means we have the variation of the excitation, the force function. So how with time this excitation is changing, we know a priori. So that is there in the functional form or whatever form. So we know the excitation, how it is changing with time, and we get the response corresponding to those time instances in the deterministic way. That means we can able to predict, okay, at this particular time, what will be the displacement amplitude or the acceleration amplitude. There are other kind of force which are called random force, and random force are like wind blowing, or maybe the earthquake, or some structure is there on the sea. So because of uh, the sea waves, the whatever the excitation is coming onto the structure, or on the bridges when a river is flowing. So that kind of random force uh, are also there, but will not be, that is not the scope of our subject, the random force. But here, when once the force is random, then we cannot able to define the force with respect to time. Okay, at this particular time, what will be the force, actual value of the force. But we will be having some idea about the what will be the statistical property of the force, like what will be the mean of the force over the time, or the variance of the force. So in the statistical form, we'll be having the knowledge of the force. So correspondingly, then obviously we cannot find the response with time. There also we need to get the response in terms of mean square response, or some what is the standard deviation of that, or some other statistical property. So, but anyway, the random force is not is the in the scope of the this particular subject. So we'll be focusing on the mainly the deterministic force. The definition of that is that we know the force with time, and then correspondingly response we get uh, we can able to get with time variation. So when we are talking about deterministic force, then we can have another subcategory of the force. So one is the forcing function, which is something like external force. Another is the initial disturbance in the form of displacement or velocity, which we are giving, like if we are hammering a particular structure. So that is some kind of velocity we are imparting at the point of hammering the point. Or if you are giving some initial disturbance and then leaving it to oscillate, so how the system will vibrate, that is another kind of. So as I told, these are actually initial conditions, but we are defining the excitation in a more general way so that it covers all aspect of the forces. Another is the moving support. Moving support is something like a vehicle is moving on a road and then suddenly some bump comes in that, and then because of that, uh, or because of the surface roughness of the road, the vehicle get some kind of excitation force. We'll talk about this moving support because most of the vehicles, when we talk about, they have the moving support because the tire run over some rough surface or some ditch or some bump, then it get some kind of initial displacement at the wheel, and that gives some kind of inertia force or elastic force to the vehicle. So we'll be covering all these forces, but we'll be knowing them with time, how these forces are changing with time. So that kind of force only we'll consider here. They will be knowing in the form of function. Uh, so this I talked about the forced vibration, that is a forcing function. This is external force which is acting onto the system. Maybe this external force can be unbalanced force, or when we are talking about engine, the because of the uh, power generation, there will be periodic forces onto the piston that will transmit to the vehicle, or the free vibration, that is the initial disturbance or initial velocity, and the moving support, the third one, in which basically there's no external force, but initially there is a displacement which gives inertia force and elastic force to the system. So to general formulation, and here initially we are taking the discrete system. So in discrete system we have the equation of motion in this particular form, and till now we have been keeping the force part as 0. Now we are adding the force qt here. Now the force we are assuming here is general force. It can be a moving support force or initial condition force or a external force. So, so this is the typical equation of motion we'll be having. This is n degree of freedom system. So here Laplace transform method is explained. So if we do the Laplace transform of this, various terms like Laplace transform of the force. So this is the force, and this is the Laplace transform definition, and this L is representing that we are applying the Laplace transform to this quantity, and this is the transformed force. So S is the subsidiary variable, and so this is the force in the Laplacian domain. Similarly, the response Qi, response is the displacement or the acceleration. So that is also transformed using Laplace transform. So we get the corresponding the displacement in the Laplacian domain. Now, if we do the Laplace transform of this quantity acceleration, so we get this s square qis, and then the initial conditions. This is the displacement initial condition, and this is the velocity initial condition. So this all will be substituting in the equation of motion. So this is the inertia part which we obtained, and you can see that now the equation is in the Laplacian domain. This directly gave us the response in the Laplacian domain. This is the force. Now we are rearranging this. We are collecting the similar terms like QS bar are collected in one place, and all other terms, including this initial conditions, I'm bringing toward the right side. So this is anyway external force, and this is the initial condition from the when we did the Laplace transform of the acceleration term. So idea is that we are representing this as a force, including the external force and the initial conditions. So now if we want the response of the system, we need to invert the terms within the bracket. So this term, so I inverted, so you can see we inverted that matrix and multiplied by the force. So these are the various kind of forces, and this is the inversion of this. And this particular this particular matrix S square M plus K is we represent by ZS, and that is nothing but the generalized mechanical impedance matrix Z. But here we have done the inverse of that, and RS we are representing all the forces. So all these forces you can see are represented as this is generalized input to the system. So with this equation, we can able to get the displacement. Just wait a minute. Yes. So we can get the displacement in the Laplacian domain, where in this I think this q within bracket 0 at time 0 or initial condition is written as q naught. Similarly, q dot, the velocity term, q dot naught is written. So this particular thing is in very generalized form. Then that inverse z I'm writing as gx, g within bracket s, function of s, and yeah, so and gs, this we already defined here. So now you can see that we are inverting. When we invert the z matrix, then in the previous classes we have seen that the adjoint of that z matrix divided by the determinant of the z matrix will give the inverse of this. If you remember, in the discrete system, we discussed this method by which by adjoint of this matrix we can get the inversion. So this is that particular inverse of the Z matrix, which is nothing but the GS. So GS is both the terms. R is the excitation, or this excitation, and Q is the response in the Laplacian domain. Now to get the response in the time domain, again we need to inverse transform this particular Q so that we can get the response with time. Here, because the force is there in very general form, so that we'll see that one by one we'll consider. So initially we'll consider only the initial condition as a force. Then we'll take this as force separately, and so even in this particular force we can have different kind of forcing, like harmonic force, which is the simplest force, sine function or cosine function, or we can have periodic force, in which if force is periodic, we can split that into various harmonics using Fourier series. So periodic force will be nothing but the summation of various forces with the different excitation frequency and their multiples. And in the linear system, we know that superposition theorem is valid. So we can take the one force at a time and get the response from that. And then we can take another force, get the response from that. So like that, one by one, these forces we can able to consider, and then we can add up the response to get the uh, response due to all the forces. So because we are dealing with the linear system, so superposition theorem will help us in doing this. Uh, so initially, now going to when we have only the initial displacement and velocity. So here we ignored the q term. We ignored that particular term here. So this you can ignore. That is, I think. So here this is same as the previous one. Only thing we are ignored the q, the external force. Only the initial conditions are there. So here there are two definitions. One is poles and zeros. Poles are generally, these definitions are there in the control systems. They talk about the poles and zeros. So in the vibrations, poles are those where the response becomes infinite, because this is a undamped system. So we can expect that we can have some frequency where this response can become infinity. Uh, Zeros are those where the response becomes zero. So that is the definition. So poles are nothing but the roots of this particular determinant. So if we are talking about this determinant, if this becomes zero, so what will happen? The response will be infinity if this determinant is equal to zero. And this is nothing but the frequency equation, which we have been talking about. So that will give us the natural frequency. So obviously, when we have the one of the so this is giving us the natural frequency, and if our excitation frequency is equal to the natural frequency, this will become zero. This will become zero, and the response will be very high when damping is there. But when there is no damping, then it becomes practically, theoretically, it will become infinite. So those are called poles, and poles are nothing but the roots of this characteristic equation we have been talking about, or the frequency equation, which gives the natural frequency of the system. So yeah, so this subsidiary variable which we are talking about, so if we take that as plus minus I omega, then because this will be a frequency equation in terms of S. So if we need to substitute this S is equal to this, so that we can solve for omega, and those will be the natural frequency of the system. So we'll get omega r, and if they are distinct, natural frequencies are distinct. These are called simple poles, and they're the roots of this particular thing. And this natural frequency will match with whatever we have done earlier. It is not key from forced vibration. What we are getting is different. This is a similar thing is there. And when repeated natural frequencies they are there, then there is another way we can able to, that is called higher order poles. So now let us do some more analysis on this. So this equation, now we are doing something more. So Z actually will be having, if we have n number of poles or n number of natural frequency. So this Z can be factorized like this. So you can see that when we are putting S is equal to I omega 1, this becomes 0. When we are putting S is equal to minus I omega 1, this becomes 0. So these are the, as I mentioned here, when we put this. So that's why this has been, because we have n number of natural frequencies. So basically, the roots of this uh, we should able to factorize. Then only independently, when we equate this equal to 0, we'll get the n number of natural frequency. And this pi capital is representing the symbol for the multiplication of these parameters. Like we have been writing the summation from r is equal to 1 to n. So here capital pi is representing that this particular term, when we are varying r from 1 to n, so those terms are getting multiplied. So you can see this first two terms will give us s square plus omega 1 square. The next two will give s square plus omega 2 square, like that. So that is the representation in a compact form of this. So this z, which is there in the denominator, which gives the natural frequency, can be written like this. So now, as I was mentioning, to get the response in the time domain, we need to do the inverse transform of both sides. So this we are doing here now, because now we have more specific initial condition. So this is representing the inverse transform of the Q bar, which is there in the Laplacian domain, and Qt is the time dependent response. So in the right side also, we have done the Laplacian domain transformation. So this is the same equation as the previous one, only thing this symbol have been added. Now this ZS, we expressed the determinant of this, we have expressed like this. So this we have replaced by this, and AS is as it is, and the remaining terms are here, the mass matrix and the initial conditions. So now we'll do some more mathematics on this to get more simplified version of this. So idea is here uh, to to simplify this equation so that we can do some uh, calculation to get the response. So this is the same thing. So you can see that we are doing the inverse transform of this. Here, the previous this I have split again in the this form. So you can see remaining terms are as it is. So I written in the complex form, and now now here it looks very complex, but now we are doing the partial fraction of this, because we have in determinant in the denominator these kind of factors are there. S is here, in the above also is there. So now we are doing the by using the method of partial fraction. So here you can see that this is the method of partial fraction, in which we can write these as constant b1, and this one for r is equal to 1. Then this is for r is equal to 2 and 3 for the negative one. Then similarly for the positive one, we can write c1 for r is equal to 1, r is equal to 2, r is equal to n. So here the idea is, because the inverse transform, when we want to do it, we should able to convert any equation into some standard form of the this particular thing, so that in the tabular form, whatever the inverse transforms are available, that can be used. So using the partial fraction, we can able to convert this particular expression in this form, where if let us say b1, if you want to obtain, so the definition of that is, I think even you can refer to the appendix in the book regarding the Laplacian transform. Hope in the mathematics course also something must have been covered about the how to get this kind of thing. So here B1, if you want to obtain QS is as it is, the whole thing QS multiplied by S minus I minus I into W. So whatever the denominator is there, we are multiplying with that, and we are putting S is equal to I omega 1 in this. So this is as it is. Q I have written from here, and here you can see initially the multiplication is from 1 to n. So I have started from R is equal to 2 to n. One term has been outside the multiplication. So now you can see that this is the same as the previous one. Only the denominator I have taken one term out, and this term and this term will get cancelled. So when we substitute this I is equal to omega 1, then this will not become 0 because they are getting cancelled. And once we substitute this S is equal to I omega 1 in this, before that I think this has been simplified by dropping this term, and then this is also similar. Yeah, this for the C1, this for the other this term. So here we have S plus IW1, so that we need to multiply and then put the value of the S is equal to minus I omega 1, and here also this plus term will cancel and we'll left with this quantity. And in this we need to substitute S is equal to I omega 1. So this will give us C1. So B1 and C1 I have shown, but then B2 and C2 and other same thing, similar procedure can be used to obtain the other constants. Then once we have the B1, B2, Bn, because here we already substituted in terms of I omega. So here it has been written that they are constant and that they have been obtained for a particular omega I1 or something. So now these are we know from the previous slide. So now if we do the inverse transform of this, Laplace transform of this, because this is a constant, so this will remain as it is. Inverse transform of this we have in the tabular form, that is the e raised to I omega 1 t. So you can see that Laplace transform of this will be, this remains same. This similarly for this I omega 2. Similarly for this second term, here because S plus I omega is there, so if plus is there, here minus will be there. So these are the terms corresponding to this, the other n terms. Now they can be sum up because these are n terms. So first n terms have been summed up corresponding to the e raised to positive I omega kt, and this is corresponding to the other c terms. And if we want to again take S I omega, the same thing can be is written that just S is equal to some variable. So if we substitute that, we'll get the same expression. And whatever I explained here, if you want general form of this is given here. So this same, it is same exactly the previous one, but if we are having a kth frequency, then we multiply that, and then this is the same procedure as the previous one. This for the CK and this for the BK. So now the inverse transform of this, which we were obtaining using partial fraction, then those steps we could able to get in this particular form. And BK and CK, we know this is BK in the previous slide, and this is CK, And here you can see that this r is equal to 1 to n, but not r is equal to k, because this has been written for the k. So this particular expressions have been put here in place of bk and ck this. So now you can see that this is the time response of the system because of the initial condition q naught and q dot naught, velocity and the displacement. So this is the final expression. So this is the final expression, and if you will further simplify this after substituting this, this slide I am skipping. This is some fundamental of the partial fraction. I think you already know, so you can go through this, how to obtain the coefficients. Some table also are given so that you know how to use these tables. So in the previous slide we obtained this was bk and this was ck. Now we want to simplify this further. So more steps we want to do it. So here one thing is there. This is the adjoint of the Z matrix, and because Z matrix is symmetric, so adjoint also will be symmetric. So, and in this particular case, we'll be having this particular thing will be valid. So based on that, we can able to combine these two like this, but there are few more steps are involved in converting this to this that I'm showing in the next slide. So here basically what we are doing, we are substituting the s I omega k in this wherever is there, and then we are simplifying this and this to get this. So this is the final expression which we'll be getting after one or two slides. So here this is the same expression. So now we have substituted in here s is equal to I omega k. So you can see wherever the s was there, we have substituted for I omega k. Even in the e raised to I omega kt. Here also we have substituted the I omega k. Similarly here we have substituted the s is equal to minus I omega k. So wherever we found the s, we have substituted that. Now because the a I omega k and a minus this are symmetric, so we can take out common from this. This mass matrix is anyway same, so it can be taken common. Here, this particular term, if you square it or you square it, both will be same, I think. This will be positive, this will be negative. Yeah, because the square of negative will be negative and square of the I will be negative. So this and this will be same, and this has been taken out. This quantity is twice of I omega k that remains inside. This quantity is twice of minus 2 omega that remains here. Here, this initial condition part and the I e raised to that thing is also there. Here also this part is here. So only the a, m, and this some part of the product we have taken out is common. Now we'll simplify this expression. We'll add this, even we'll expand this e in terms of sine and cosine. So this is the same expression. Now we have summed this up so that this get multiplied by the this and cross product, and this e raised to omega t also we expanded like this using Euler equation cos omega t plus I this, and this minus 1 is here. So if you expand this, multiply, and you'll get some terms will get cancelled, and you'll get then simplified form of the equation like this. Denominator remain the same. A negative thing have been incorporated in the numerator part. So this further can be simplified. So if you expand, this can be finally whatever earlier I showed, this expression we can able to get after simplification. So if you see this expression, this is the response due to the initial disturbance Q naught and Q naught dot, the velocity term. This is the harmonic functions are there, and we represented the omega k as the natural frequency of the system. So because of the initial disturbance, because these are the constant quantity, so because of the initial conditions, we'll be having motion which will be harmonic in nature, and their frequency will be equal to the natural frequency of the system. And depending upon the initial condition, the harmonic frequency or the natural frequency, either all natural frequency can be there or some of them can be there. So that is a very important thing, that any dynamic system, if we disturb it by giving some initial disturbance in the form of displacement or velocity, the frequency at which it oscillates will be one natural frequency of the system or combination of natural frequencies. So there will not be any other frequency apart from the natural frequency in the response. So there is very important conclusion from this, that when we excite a system uh, due to the initial disturbance, always it will be having uh, the harmonic motion, and the frequency of that will be a single natural frequency or combination of that. And depending upon the initial condition, it may take uh, several frequencies also. Generally, if we are exciting by impact, then the impact is having impact gives various kind of the natural frequency can be excited through the impact in the system. So generally, when we want to obtain the experimentally the natural frequency of the system with a so-called calibrated hammer, we tap the beam or whatever the system is there, and we measure the acceleration or the displacement of the system, and then that's just the whatever the signal we got. If we see in the frequency domain, we can able to get the frequency content of that particular signal, which will be containing mainly the natural frequency of the system. So whatever the, I think, video lecture I have sent regarding the lab, if you see back those video lecture, you can able to appreciate that how we can able to obtain the natural frequency of a beam, or a beam with two disk or three disk, using the so-called fast Fourier transform. Directly through instrument, we can able to see them. So the motion will be the superposition of harmonics. It depends upon the various initial conditions. So here we don't have the any steady state force, and generally when we have this kind of initial disturbance, because of damping in the system, because in any real life system there will be damping. So this kind of disturbance will dies out after few oscillations. So system will oscillate maybe for few seconds, and then it will stop because of the damping. So when we are talking about this kind of oscillations, so generally we talk about vibration for a short duration. Uh, Short duration means few oscillations, 5 oscillations, 6 oscillations, depending on the system damping. And yeah, so this is the if damping is there in the system, then the S which we have been writing only the if you remember, we wrote S is equal to I omega k, but if a damping is there, then S will be having real part also. So that the zeta is nothing but the damping. This is the damped natural frequency, there is undamped natural frequency. And this kind of response which we get from the initial disturbance is called the transient. They are transient in nature, and we need to consider them for short duration. If there is a external force also along with this initial disturbance, then because the external force when is there, that will be there for forever in the system. So when we want to obtain the effect of the external force on the response, then this transient part we need to ignore, because this transient will be there maybe initially for a few seconds, then it will not be there in the system. Only the response due to the external force, steady state external force will be there. That we call it steady state response. And the next is that only the response due to the harmonic excitation. So if you remember, we in the Laplacian domain, we express the response like this, in which the force was having initial disturbance and the external force. In the previous case, we ignore the external force. In this particular case, we'll ignore the initial conditions. Because it is a linear system, if we want to obtain the response due to combination of this, we can superpose this. So we whatever the response we obtained earlier can be added to the response obtained because of the external force using the superposition theorem. So that can be used directly. So here now we are ignoring the initial condition because we have already obtained the expressions for that. Only we will consider the external force. So external force, here we are considering the simplest force. There is the harmonic excitation. Harmonic excitation is is uh, is some kind of sine functions or cosine functions. So this is the force represented. There are n number of force in the system. So it is very important that there are n number of force, and all the force are having different frequency. Capital omega j is the frequency of the system, or the external force. Capital omega j is the external force. Small omega, which we discussed earlier in the previous slides, that is the natural frequency of the system. So this capital omega and small omega, if they coincide, there will be resonance condition. Okay, so that is we'll see how the resonance condition will come. But this we are assuming that this particular excitation force is away from the resonance, let us say, and that's why we are writing distinctly, and at different locations their frequency is different, also the amplitude is different, and this amplitude is nothing but the complex amplitude. What is the complex force amplitude? If this is a complex number, so the complex number is a vector quantity having the magnitude and the phase. Magnitude and the phase. So that means because the different force can have different phase lag. So this particular complex quantity will take care of the phase lag among various forces. So, and here, because this force is a real quantity and we express this in a complex form, so only here our interest in the real part of that. Just for mathematical convenience, we written in the complex form. Actually, the force is in the real form, and we have converted them in a complex form just for convenience. So when we get the response in the complex form, we'll say that we are interested in the real part of the quantity, whatever we obtained. In between, we'll not talk about the real part. That is the understanding that we have the force, which is actually real number, and because of the mathematical convenience of this, in the complex form we have written. Once we get the response, then we'll take the real part of that, so that the imaginary part will ignore it. So this is the force is having some circular frequency. They are not natural frequency. Again, I'm repeating, this is the external force frequency. Like if there is a unbalance in a rotor system, then the circular frequency will be equal to the angular speed of the rotor. So that is called circular frequency. Circular frequency is generally in the radians per second. So this particular n number of forces we can able to put in a vector form. All forces we are combined in a vector form. So is here now the subscript j we have removed here. So okay. Now if you do the Laplace transform of this force, because this is a constant term, is not time dependent, only the Laplace transform of this we need to do, and the Laplace transform of this we know is equal to this. So constant is same, only thing is this. So if we take one of the term, that is q naught 1 s minus I capital omega 1 is for one of the force, is for second force, this for nth force. So this is in the vector form, this is in the expanded form. And this transpose represent that is a column matrix, a column vector. Okay, so if you go back to this equation, R, this is the transform of the force. So this is the transform of the force can be replaced by this quantity. So here we will replace this R with this. So I'll stop here. Now our aim will be to obtain the inverse transform of this so that we can able to get the response to this harmonic force in the time domain. So that will be the next step, which I'll be covering in the next class. So if you have any questions, you're welcome for the questions. Okay. Okay, so regarding the quiz, there was some issues, so I shifted them in the last week, 24th and 27th. Anyway, it was there. So fourth quiz will be on 24th and the last quiz will be on 27th. So with that, we'll conclude our semester. So if you don't have any questions, yeah, Manpreet Singh. Manpreet Singh.
Yes, sir. Yes, sir. Good evening, sir.
Yes.
Sir, as you said, like in undamped case, the response to initial condition will be having time period equals to natural frequency or combination of natural frequencies.
Yes.
So, in case of damping, it will be equal to damped natural frequency, like that.
Yes. Yes. It will be damped natural frequency.
So, sir, as you said, means in experiment, in lab experiment, we got it reversely. I mean, by noticing the response to initial conditions. So, in that case, we will also have to consider that damping effect.
Damping is already there in the system.
So,
No, damping
means
is already there in the system. So once the damping is there in the system, we cannot get the undamped natural frequency unless we obtain the damping also from the system. So that also we can able to obtain damping of the system.
okay,
So
means experimentally we can obtain damped natural frequency.
Then with if we know the damping, undamped natural frequency can be obtained. Okay.
Okay, sir. Yes, sir.
Yeah. But resonance will take place at the damped natural frequency.
Okay.
Yeah, because undamped is our idealization
Yes, sir. Means
for mathematical convenience. Because once damping is there, then the complexity in the mathematics is the eigenvalue is complex, eigenvector is complex, So then interpretation becomes more difficult. So that's why, and the with damping, natural frequency changes very little. So we are not getting much by introducing the complexity. That is the main thing. Okay.
Okay, sir. Yes.
Another aspect regarding the damping is we cannot able to mathematically model the damping. We need to obtain experimentally. So if you're talking about a beam,
Yes, sir.
so we cannot mathematically say if this dimension or this material property there, this will be the material damping, this will be the damping of the system. We cannot predict. We need to actually do the experiment and then we can do it. There are some approximate models are there, approximate models, but they are not reliable. Okay.
Yes. Yes, sir. But
Any other questions? Okay, so if there is no question, I am stopping the video.